Hi, I'm Will Krozik, Scientific Services Manager at Chemical Computing Group. Today I'd like to show you how we can analyse a protein-ligand complex. We'll do that by looking at key interactions, steric fit and hotspots, and then I'll show you how we can use that information to design a better inhibitor and improve its properties. So let's get started. In today's workflow, I'm going to focus on using the right-hand side button bar. This has been streamlined specifically for structure-based drug design work, so I can use this to access the Open button, and from here I'll be able to navigate to the file that we're going to be working on today. Once I select that file and hit OK, I'm greeted with this Load PDB file panel. This allows me to select what data I'd like to load into Mo. Here I'll accept the defaults, and that loads in our structure, EGFR kinase with a ligand called Tasiva, which is bound. You'll notice that the receptor has been coloured by its secondary structure. So we've got our beta sheets in yellow, helices in red, and turns shown in blue. To get a better view of the ligand interaction with the receptor, I'm going to hit Site View. That isolates the ligand together with any residue within 4.5 angstroms. And next, given that we've just loaded a raw PDB file which typically doesn't have any hydrogens or charges calculated, perhaps it's missing some loops. So before we start any interactive modelling or analysis, we need to first prepare our model. So for that, I'm going to use Quickprep, our automated preparation wizard, comprising three main sections. The first handles preparation and cleanup of the structure. Second sets tethers and restraints. The third handles refinement. So again, I'm going to accept the defaults. I click OK, and I get a message at the top left of the main Mo window telling me that the calculation has been initiated, and it also gives me a progress update. Now I'd just like to take a moment to reopen this panel so that I can explain what's going on in the background. The first preparation stage ensures that we have a complete model. Here we're adding in missing hydrogens, charges and side chains. We'll also build any missing loops up to 10 residues in length. Proteinate 3D optimizes the ionization states of the bound molecules and their side chains. It also optimizes the placement of polar hydrogens so that we can generate a hydrogen bonding network. By default, we tether atoms within the active site, and the reason that we do that is to ensure that we can retain the original geometries of those atoms as captured by crystallography. We don't want to lose those to processes such as energy minimization, so for that reason, those atoms are tethered. Likewise, any atoms that fall outside of the active site are fixed, and we can do that for reasons of computational efficiency. The final refinement step performs an energy minimization to ensure that we don't have any clashes in our structure. I see the message has gone from the top left of the main Mo window. It tells me Quickprep is complete, so now that we have a prepared model, I will cancel that and move on to introduce the system manager. So I'll just pin the system manager to the main Mo window as a means to control all of the data that we have in the system. From here I can hide and show different atom sets, I can make selections, I can also render and generate surfaces. Within the system I see that we've got receptor, solvent and ligand, and next, in order to make everything easier to see, I'm going to set the rendering of our system using the system manager, first hiding the ribbon, and secondly rendering the ligand a bright colour so that it stands out. Next, I'd like to adjust the hydrogens display. Currently we're displaying all hydrogens, so I'm just going to use the hydrogens button and toggle between showing all hydrogens to no hydrogens to get to my preferred view of the polar hydrogens. And with the view set as I'd like, and having prepared the model, we're now ready to familiarise ourselves with Tasiva's interaction with the EGFR binding pocket. And based on that analysis, we'll see if we can modify it so that it becomes more potent. The first place I look for that type of analysis would be the main Mo window itself, and I can see that Mo has automatically calculated and annotated the classical hydrogen bonds, which are shown by these dotted lines with a cylinder in the middle. I'll just mention that Mo can also calculate non-standard interactions such as proton-pi, halogen and sulfur interactions. Now the size of these cylinders are important because they give us an idea about the strength of the bond. The longer the cylinder, the stronger the bond. If I want to quantify that, I can use the bond rendering tool to be able to toggle between the bond strength in kilocalories per mole to the bond length in Armstrongs to displaying that hydrogen bond as a simple plain dotted line. And I'm just going to toggle back around now to my preferred cylinder view. So using this type of analysis, we can quickly identify that we've got 1, 2, 3 classical hydrogen bonds, and the only interaction or specific interaction between ligand and receptor occurs on this canazoline core. I can see that one bond is much stronger than the other two, and I can see that one of the bonds is acting through a water molecule. So I can see we've got a water-mediated hydrogen bond here. Now, if I wanted to get an understanding of which residues we're interacting with in the receptor environment, I'll go ahead and open a ligand interaction diagram. So this opens a 2D schematic of our ligand together with the interacting residues. I get a key at the bottom that helps me understand the graphic, but at a high level these green residues represent those that are greasy or hydrophobic, the purple residues represent those that are polar, and where I see the blue cloud, it represents that our ligand is exposed to solvent. I find that a 2D diagram is a great place to go to when I want to start to understand any ligand-receptor complex and the scope that we might have for modification. Here I can see those same 3 interactions that we saw earlier in 3D, but perhaps the most important part about this diagram would be the dotted line. The dotted line represents the binding pocket, and the reason that it's important is because it gives us our first clue about steric availability. I can see here that the ligand is very tightly packed to the receptor around the canazoline core, so there's no chance to make a substitution. The same can be said for this triple bond region. But as we move around the dotted line, looking at the rest of the binding pocket, we see a bit of space around this ring system, suggesting we might be able to fit a substitution in around this region. And in fact, the dotted line becomes broken as we head out towards the mouth of the pocket where the ligand is exposed to solvent. Given that we have no specific interactions on these polyether chains, perhaps this could be an area to improve our ligand design. We've made a good start analysing this, but let's go a step further by having a look at this in 3D, and for that we can generate some surfaces. You'll note the quick access surfaces that we have available in Mo. I'm going to start by generating a receptor surface. This is going to give me an idea for the binding pocket size and its shape. So this particular surface is coloured by atom type, predominantly grey for the carbon atoms, but we pick out the reds and the blues corresponding to the oxygens and the nitrogens. I find that this surface type is particularly useful in identifying hydrogen bonding opportunities for ligand design. We can identify those hydrogen bonding opportunities by either cyan or white patches. Deep in the back of the pocket here we see a white patch which represents polar hydrogens. In this case the ligand has utilised this hydrogen bonding opportunity. But conversely I can see many cyan patches around the mouth of the pocket. The cyan represents lone pairs, and these are unutilised opportunities. The ligand has not or does not currently utilise these interactions. So another clue that perhaps we could target one of these lone pairs. We can further explore the interactions by generating another type of surface, this time an interaction surface. It gives us more clues about how well Tessiva fits in the pocket and how it could be optimized. I'm using the interaction surface as it tells me about the steric fit of the ligand. The way that I can interpret this diagram is where I see the heavy atoms of the ligand touching or almost touching the edge of the grid. That tells me that we've got an optimal steric fit in that region. it's true of the canazoline core, and if I roll our ligand round, it's true of the triple bond. Now, if the ligand was to protrude beyond that grid, it would indicate that we've got a steric clash. That's not the case here, but conversely, where we can see that there's a gap between the heavy atoms of our ligand and the edge of the grid, this tells us that we've got an opportunity. It's an opportunity to optimize the ligand design by placing atoms on that surface. So I see we've got such an opportunity around this ring system. If I just rotate our ligand around, we've certainly got a lot of opportunity around the mouth of the pocket and these two chains. Now, while we're talking about steric availability, I'd like to introduce another tool which can help us understand more about how and where to grow a ligand. So that's using a tool called R vectors, and I'll just toggle those on. And when I do that, you can see that our ligand becomes annotated with these green arrows. The green arrows show us where we can make a substitution around the size of a methyl group, but without creating a steric clash. We see many such opportunities on the chains, as we would expect, but it reinforces that we don't have any available on the canazoline core, that's already well optimized for the receptor environment. So already we're building a good idea about where to optimize our ligand. The question then becomes how. How much bulk, what kind of groups do we need to think about using? Unfortunately, Mo has some tools to help us answer those questions. For that, we can call upon electrostatic maps, which I can access from the Surfaces and Maps panel. This is the main panel for all molecular surfaces created by Mo. The panel is split into three, where at the top we have a list of any surfaces we've already created. In the middle we have options to generate new surfaces, and at the bottom we can edit existing surfaces. So I'm just going to move this to one side, and I'll start by hiding our existing surface, and then I'll go ahead and generate that electrostatic map. So the electrostatic map creates interaction hotspots. It's giving us information about the receptor, not the ligand. It tells us where the receptor would like to see an interaction, and it tells us what type of interaction the receptor is looking for. So this is all useful information in understanding how to design a ligand. In the main Mo window, we can see that we've got white, red, and blue hotspots corresponding to the hydrophobic, acceptor, and donor hotspots. So let's go through these one at a time, starting with our white hydrophobic hotspots. Here I can see that the ligand is touching the hotspot and it's got the right type of interaction. So this tells me the ligand is already well optimized for the hydrophobic interactions in not just one, but in two places. If I just zoom out slightly, we can see that there's a third hotspot, but it sits just outside the binding pocket, so I won't concern myself with that. I'll conclude that there's nothing to do to optimize our ligand for a hydrophobic interaction, so I'll move on and have a look at the red acceptor hotspots. So again, I can see that we've got 1, 2, and 3 hotspots, with others sat outside of the binding site. Again, I can see that the ligand is satisfying the hotspot in the sense it's touching and it's got the right type of interaction. That's true again in 1, 2 places. This third hotspot here is actually occupied by the water molecule, so that tells me that that water is complementing the receptor environment. Again, I can conclude that we don't need to optimize our ligand for the acceptor hotspots, and I'll move on to analyze the donor hotspots. This type of hotspot is unique. Here we can see that the ligand is not touching any of the hotspots, let alone having the right type of interaction. So this is another clue that perhaps we can optimize our ligand design for an interaction with one of these donor hotspots. But before we get into that, let's just quickly recap that during the analysis of the deceiver EGFR complex, we firstly used the receptor surface to identify lone pairs and potential hydrogen bonds. Then we used the interaction surface and R vectors to identify steric availability. And now we've used electrostatic maps to identify an unsatisfied donor hotspot. At this stage, we can say that we're finished analysing Tessiva and we're ready to use this information to design a better inhibitor. Our strategy will be to leave the design of the canazoline core alone because we saw that that's already well optimised for the receptor environment. But we can certainly build out these side chains for better interactions, hopefully picking something up with a donor hotspot. In the process, we're going to be recreating a potent inhibitor, a known analogue of Tessiva. I'll just hide our surface, and before I go ahead now and actually modify the ligand, it's always good practice to take a copy of that original co-crystal structure. That way I can refer back to it if I need to. So I'll just duplicate our ligand entry, and I see that second entry appear now in the system manager. The second entry is grayed out and it's got an I next to it. The I is significant because it tells me that it's inert, and that means it won't be considered by Mo in any of its calculations. So that I'm clear on which ligand I'm modifying, I'll just change the colour of the active copy to be cyan, and the next thing that I'll do is, as we start to modify this cyan copy, we'll want to keep track of its properties. So for that, I'll toggle on the ligand properties, which are displayed in the top left of the screen. These properties describe bioavailability, so you'll see parameters in there such as molecular weight, a prediction on toxicity, and these are all updated on the fly. They reflect any changes we make to the ligand structure in real time, so we can keep an eye on these numbers and ensure that the ligand we design is also bioavailable. Next, I'm going to hit minimize, and the reason that I'm doing that is to allow the system to calculate these three additional properties: strain, solvation, and affinity. These are calculated every time I click minimize. And I'll just take a moment to elaborate on affinity. It's the measure of how well the ligand is interacting with the receptor environment. It's an energy, so the more negative that number becomes, the better the interaction. Next, what I'll do is introduce the builder, and I'll just pin that to the main Mo window because it contains everything that we need to be able to create our analogue. We get a list of atoms, bonds, charges, functional groups, and ring systems. So with that, we're ready to start modifying Tessiva, and we'll start by deleting these two chains. So I find the easiest way to select those atoms would be to raise a 2D schematic of our ligand, and then I can simply drag a box over the atoms that I'd like to delete, and then I'll click delete on the right hand side button bar. I notice that the R vectors get updated due to the space that we've just gained there through that deletion. So next, to create our donor feature, I'm going to add an NCO group at this R position that's been suggested by the R group vector. So I'll click NCO in our builder, and I see the NCO group is added at a sterically uncongested conformation. Perhaps this dihedral, though, is not quite optimal. So I'll go ahead and select the bond, and I could control the dihedral by using this scroll wheel that we find on the footer, but an alternative way to do that would be to use the dihedral plot. Here we see the dihedral plotted along the X, energy along the Y. The solid white line that we see here represents the energy within the binding pocket, with a vertical green line showing us the current dihedral. So this reinforces that that group was added at the sterically uncongested conformation, or in other words, the local energy minima. The dotted line in the background represents the the energy of the ligand in the absence of the receptor environment. And these blue histogram bars leverage a program called Mogul. This performs statistical analysis of similar dihedrals of many small molecule crystals, and it's telling me that the typical angle for this type of bond would be either 0 or 180. So I'll just click 180 since that's the closest to our current angle, and we see that that bond moves now in the main Mo window to reflect that selection. Now, because I've added a functional group and I'll want to recalculate my affinity, I'll hit minimize on the right hand side button bar, and that allows the ligand to relax in the presence of the receptor environment. So after minimizing at 180 degrees, we go roughly back to the starting point, which is telling us that for this specific example, 180 degrees is not optimal for this specific molecule in this specific receptor pocket. However, we didn't need to worry about it because the minimization process took care of all of that for us. Next, I'll continue to modify our ligand. So what I'm going to do is just select again the R vector, and I'm going to add 3 carbons in this position. Because I've added some groups, I'm going to minimize as I go along. And then I'm going to add a nitrogen and a charge to that nitrogen, and I'll minimize once more. And with that, I'm done building our ligand, so I'll toggle off the R vectors, and I'll just recalculate our site view now. So in this case, we've been modifying our ligand to arrive at the structure of a known analog. But what would happen if we didn't know what groups to add or where? So for that, I'm going to show you how we can modify a ligand using substituents from fragments. So we can show that on this triple bond region just here. We saw that that was a sterically congested region. So for that reason, I'm going to select the bond and delete it, just to create a bit of space. And then what we'll do is investigate what fragments could fit in this region here. So I'll press fragments in our builder, and then we see that a list of substituents appear in the builder menu that would fit in that receptor pocket. They're listed in terms of the most energetically favorable first, and I can use these arrows now to have a look at that favorable, the OH group, which is most energetically favorable. If I can just click through to have a look at the different conformations of that first group, or I can click through to have a look at some of the other substituents that would fit in the pocket. So in this case, I'm going to select the bromide group and again minimize in that position. I'll just recalculate the site view, and at this point what I'd like to do is bring back our original co-crystal ligand. So I'll just click on that so that we can see Tessiva shown in magenta against the analog that we grew in the pocket shown in cyan. You'll notice that we've been able to preserve the canazoline interaction that we saw was optimal, but overall we improved the interaction of our analog shown in cyan. If I just toggle on my electrostatic map, you can see that we actually built out to hit one of those donor hotspots, and we managed to take advantage of that charged amino group with that interaction. There's also a second interaction here on the carbonyl, and you'll notice that both of these interactions were not present on the original Tessiva. So that brings us to the end of today's session. Today we saw how to analyze a protein-ligand complex using this right-hand side button bar. We did that by looking at key interactions, steric fit, and hotspots, before using that information to design a better inhibitor and improve its properties. I hope you've learned a lot today. If you have any questions, please reach out to me at support@chemcomp.com.